about the normal distribution. It says, oh, it's important for all these reasons. And it says, the normal distribution provides the basis for classical statistical inference because of its relationship to the central limit theorem. What does that mean? That means that it's going to just show up in the rest of the chapters. So even though it looks like, oh, we're just going to learn how to use continuous distributions just like we did discrete ones last week, this normal distribution is going to be your friend for the rest of the class. So pay attention to it and understand what we're talking about. And the book has a lot of pictures, a lot of good examples, so I think it should be clear. But anyway, there's more to this. This is coming. And in fact, they're sneaky. You know, they're doing these little playing with your minds. If you look at the problems they work and the ones I work in class, they're picking, it appears like they're just kind of randomly picking some values that work out to certain positions on the normal distribution. But those are ones that correspond to very common things you're going to use when you get to the inference. So they're already trying to, subtly, influence your brain and things like that. So anyway, this is a critical chapter, even though it just looks like more on distributions. So the normal distribution, I put on a smiley face because it's just used in statistical inference. It's used all the time. Everybody, noise and all sorts of processes, grades, things like that are often normally distributed. And one of the things we'll do in this chapter is we'll look at how do you tell if your data are normally distributed, because you don't want to make that assumption and then it not be. And there's an easy way, the normal probability plot is really easy to do. The exponential distribution, a lot of times people use it for time between arrivals. So we'll just kind of touch on it. It's in there, they discuss it, that's fine. The uniform distribution is where you just got low to high, an equal probability between two numbers. So you can see how you would use that to model a lot of things that you don't know a lot about. Well, I got a minimum time and a maximum time that something can be done. Okay, and equally probable in between. And I'll mention too, a lot of times it's used as a seed for these other things, and I'll tell you in a minute how it might be. And then the log normal distribution, oftentimes service times. And so we'll know that, but then we'll focus a lot of our attention on calculating probabilities out of this one, because that's what you'll wind up using in the rest of the course. And so, is this stuff any good? Yeah, I used it yesterday, and you might use it all the time. I was working on that problem where we've got we're trying to detect things that are energized when they shouldn't be, like a light post or a fire hydrant, and they asked the question, well, when we go and do these tests in the field and we set our sensor right at the edge, right at the point where it might detect or it might not because the electric fields are getting low, what's going to be our probability of detection? And because you're going to set the sensor there and you're going to, do this number of times, move it by these objects several times. How are we going to evaluate this? So I made a little model where I had my energized object. I just used our equation that we had from the lab and used the normal distribution to add some noise to it, so it acted like the voltage was varying. And then I used, for the distance away, I used a uniform distribution, just put it in between two spaces. So, we put the sensor either here or here. There's a small variation, but the fields drop off by 1 over r cubed. So a foot or so could matter, especially a sensitive sensor. And then I went and used the normal distribution again on the end of the sensor to say, well, its detection capability fluctuated too. And then ran 1,000 cases, did all this in Excel, ran 1,000 cases, analyzed it with our little, probability, with the technique you'll learn in chapter 7, and gave them an answer. Hey, look, depending on if you're right at the edge and depending on how the fields vary and these values of this uncertainty, you might only detect 50% of the time when you're right. And so you can come up with an answer. Actually, I came up with a confidence interval, which we'll learn how to do, and I gave a minimum and a maximum. So this stuff is useful, and you can do some things with it. I can answer that question in an hour. And part of being able to choose from a normal distribution, I use this as a seed to it, and you'll see how maybe when we get to class. It's not important. It's just the important thing is that this is useful and current. You can use it all the time, and then we'll use the normal distribution in inference constantly. So anyway, I think this is pretty clear stuff. Let's see what you think. I've got 2 or 3 problems to work at the end that help clear it up too, and I'll draw on the board with them also to help illustrate what I'm doing, as well as I've got the by hand version and the Excel version both. So first, yeah, let's start, we're doing continuous variables. Remember last week we did discrete, things that you could count, 2, 3, 4, 5. Here we got continuous things that you measure, length, times, temperature, height, all those things that can potentially take on any value. So that's the difference between this week and last week. So hey, let's jump right in. The normal distribution, that's the old bell-shaped curve, right? That says, and what do you mean by bell-shaped curve? What in the heck is that anyway? Well, that's an illustration, if you will, of the probability of taking on that value. So the average, the mean here is right in the middle. It's most probable that you will take on, if you have a sample measuring the height of 20 zillion people, or you're pulling a sample out of your production process, or you're doing something else, that it's most probable that you'll have this value of the mean. But we also have the standard deviation to measure, how much we vary about this mean. And so, clearly, you'd have a difference. I guess it's probably on the next slide, I think, yeah. In fact, where's my preview? I like that. So when I say it's probably on the next slide, I guess it's not doing that today. But you can see, you could have different normal distributions for different means and standard deviations. Like I said, we'll see in a minute. And the random variable right theoretically has an infinite range, minus to plus infinity. Now, we all know that, you could theoretically get any value the way that's distributed, but the tighter the standard deviation is, the more likely the values are to occur around the mean. But be careful if you do wind up using a bell-shaped distribution in some sort of little model. You put it in Excel, you calculate something, and you put the mean close to 0. There is and you don't have too tight a standard deviation. You can get some negative values, which might make your whole model blow up if, say, it was time or distance or something, and you couldn't, or mass. You can't have a negative value. So if you do wind up using it in something like that, make sure that you are aware that, you could get a negative value. Don't do that. Calculate, make you a little if statement that says, hey, if it's negative, put 0 in or something. Deal with it, because it is theoretically possible that it can get down there. So this is the equation for that shape. Now, you can look at it and say, okay, I'm done with that. I don't have to do any more with it. And you can be fine. And that's what you should do, I think. But at least look at it, because how sometimes the math nerds always have it on their shirt, and it says, I'm normal, but the shirt doesn't say I'm normal, it says I'm, and it has that, you're like, what? Yeah, so that's what they're saying, yeah. Where does this come from? Some interesting math. And you know me, I can't leave it to just say, hey, it's interesting math. So I did put it on here. Yeah, it's on the website. Here it is. A really pretty slick derivation of where that comes from. And they relate it to throwing darts at the origin, and they make a few kind of weak assumptions about, well, the amount of darts that land over here is unrelated to the amount that lands over here, but that more will land in the middle, because you're trying to hit the bullseye. If you're interested, that's posted, read it. I see no use in going over it in class, but it'll show you precisely and exactly where this equation comes from. But suffice it to say that, hey, that's just the equation for the height of that bell-shaped curve with a mean of mu and a standard deviation of sigma. And it's not obvious, but that's okay. We don't care. We can use it all day long without having any idea where that came from, or you can read the little derivation. Yeah, here we are. So if you change the mean and you change the standard deviation, you're obviously going to get different bell-shaped curves, right? These two have the same mean, the yellow and the blue one, but they have different standard deviations. The yellow one is less, it's tighter. The magenta one has a different mean and a much broader standard deviation. So you can see we have an infinite set of these curves. For this mean, this standard deviation, that standard deviation. A whole infinite set of them. Well, that's done, right? We don't want a book with an infinite set of curves in it that we got to look up. So anytime you've got this infinite set of solutions or parameters, things, what engineers always do? They always jump to doing something, normalization, right? Let's normalize it. Let's divide by something and let's put it all on one curve. So, well, gee, that's what the standard normal distribution is. they're going to take it and they're going to normalize, and instead of just having some random variable x, well, they're going to reference it to the mean and divide by the standard deviation. So that's your normalization, so that we can take all of these infinite number of curves and cram them into one. Yeah, that way we can have one table and one function. And so that's, and they'll say that in these next few curves, yeah. Yeah, we'll get there. So let's see, yeah. Changing sigma makes it spread more. Changing mu puts it in a different place. So let's see here. Yeah. Yeah, so any normal distribution with any shape can be transformed to the standardized one with this magic transformation, right? Position it mu, and you scale it by the standard deviation. So let's see, did I actually? Oh no, here it says, yeah. So the standardized normal distribution, they're going to position it at 0, at mean of 0, and they're going to let it have a standard deviation of 1. And we're going to reference all of our samples to that, just using this normalization. Let's see, yeah. So you translate x from your average to 0 by doing this. Your average is mu, so yeah, you're going to move it over there, and then you scale it. You had a standard deviation of sigma. If you divide your whole distribution by sigma, now you've got a standard deviation, if you will, of 1. Yeah. So now you're in the z world. It has a mean of 0 and a standard deviation of 1. So now when we ask any question about a normal distribution in your particular normal distribution, you just make that transformation, and now you can ask that same question of the z, the standard distribution, and answer it with those tables or those functions, and then translate back if you need to. And we'll show you exactly how to do this. There's a bunch of examples. The book has them. So now, so what they're doing here, they took that probability density function and said, what's it look like for the standardized normal? So they just let sigma be 1, mu be 0, and that's all they did. Again, we don't care. We'll use it without having to have any knowledge of the density. Yeah, there's a picture. Oh, but one thing I do need to mention about these, so you'll know, since it's the probability of z or x or whatever it is occurring, right? It's very improbable that you got low values here. Very highly probable that you're going to take one of these values. The whole idea is that you've got to have something happen. If you went from 0 or went from minus infinity to plus infinity, you will obtain some value. So the sum of these probabilities, which is represented by the area under this curve, has to be 1. Some value, you have to have a probability you're going to get one value. They'll say that in a minute too. So let's see. So here's an example. So we think we've got a variable that's distributed normally. It's a noise, it's some function that throwing darts at the board like we said. And we think it has a mean of $100, all right, and a standard deviation of $50. So what's the z value for $200? So what they're saying is you've got some normal distribution that sits over here with a mean of $100 and a standard deviation of 50. Okay. And then we're asking ourselves, well, what about this point way over here at 200? Okay, so with $200, and we're asking ourselves, if we put that in the z world, and I want to translate that into the distribution that sits right here at 0. So what is this z out here that corresponds to 200? That's all they're asking if you did that. So hey, mathematically, x is 200, my mean was 100, my standard deviation is 50, so z is sitting at 2. It's equivalent to saying that, hey, yeah, 200 is 2 standard deviations away. Well, yeah, it is. So it's 2 standard deviations away, so in the z world, z is equal to 2. So now we can use that, yeah. Now 2 standard deviations, 2 increments of 50 above the mean of 100. Yeah. Let's see. Oh, well, I should draw a picture of it for me. I did. Yeah. So here's the x world, here's the z world. Yeah, the shape is the same, only the scale has changed. So we can either talk about the problem in the original units, X dollars, or in standardized units, Z dollars. The book does a nice job too of describing this, showing you pictures. They've got a nice picture in there of the standard normal distribution and two other normal distributions, and they're translating it with little lines. Nice illustrations. If the words don't grab you, take a look at the book and see their little pictures and stuff. Okay. So now we want to use this. Now we've recognized where are we at? We've recognized that we've got a zillion different normal distributions based on the means and the standard deviations, but that we could transform to this standardized normal. Okay, so we can transform them to that. Now let's start using them to get some probabilities. What do you mean? Things like the introductory little setup in the chapter where they said you've got an internet service and you're downloading videos and you find that it's normally they come at 7 seconds with a standard deviation of 2 seconds. What's the likelihood that, how long is it going to take 99% of them to download? What's the, how much time is it for 10% of them to download? So questions like that. What's the probability that something will take 8 seconds to download? These kind of things. So the first thing you have to ask yourself is how would we figure out probability? Well, probability is the area under the curve. That function was the probability density, how dense it was. So if we got a density, we're going to have to multiply by an area, or if it's if it was a density, the mass sense, you multiply by volume. So therefore, that in a continuous thing, mathematically, these guys say, well, therefore, since it's the height basically times the area, the probability of achieving any one value is 0. It has to have a little range around it. That's the mathematics speaking to you. I don't ever worry about that. Okay, yeah, right. Mathematically, as you get infinitesimally small, they make that arguments like Zeno's paradox and those kind of funny things that mathematicians always tell you. Just know that, hey, the probability of obtaining a value between A and B is this area right here, this green area. Okay, so the probability of obtaining any value from minus infinity to plus infinity is 1. So the area of this is 1. So if we wanted the probability of not being in the interval A to B, it would easily be calculated as 1 minus the area. And remember that kind of thing, because we're going to use that a lot. Yeah?
Is this just the easy way to get the integral? I'm confused. What's the relation here? We took an integral.
You could take the integral. In fact, mathematically, that's what it is. Now, we won't do that. We won't be taking any integrals because the tables will do that for you. But yeah, if you look at it as expressed mathematically, that's precisely what they're doing. They're integrating that 1 over square root of 2 pi sigma e to the minus, I forgot what's up there, the x minus 1/2, let's see, x minus mu over sigma, right? Squared, I think. They're integrating that with respect to x and to get that area.
Isn't density divided by the
right?
volume
So density really is your probability divided by the area.
Okay.
So if you multiply it by the area, or if you integrate it with respect to area, you get the whole probability. That's what they mean when they say probability density. Yeah, what's the probability in this area or this region or for this range? But we won't care. When we get ready to use it, we will use tables or we'll use Excel where all of these probabilities are already calculated for you. And in fact, what the tables show, they'll do this interval from minus infinity to a particular value. Okay? So they'll add up the whole probability from here to there. So for example, if you're asking, and you'll see this in the example, I'm going to work a bunch of them. If you want to know the probability from A to B, you'll just get the probability of B in the table and the probability of A in the table, subtract the two. Yeah. Now, if you want the probability that's greater than B, well, you get the probability of B and subtract it from 1. That's all you do. And we'll work several of them to show you how that works. They'll work some. In fact, that's what's coming in the next slide. So they're trying to cover themselves mathematically by showing you this and showing you that's an interval. But then when we get to using it, we'll just be looking them up out of tables and relating them to the probability and using that probability to make decisions or answer questions. Yeah. So logically, since this distribution is symmetrical and the probability of something happening is certain is 1, well then half of it's on this side and half of it's on that side. Yeah, so you see how they're writing things too. The probability of minus infinity up to the mean is 50%, and the probability from the mean all the way to plus infinity is 50%. The overall probability is 1. Regardless of whether it's a regular normal distribution or the standardized normal distribution, all of them are the same. You know, they all have a probability of 1 if you go from minus infinity to plus infinity, and they're symmetrical. So let's see. Yeah, so here's that example that we had a minute ago. When we said we were looking at the $200 relative to the $100 mean and the $50 standard deviation, and we said Z was 2. So if you ask yourself, what's the probability of a number being less than that? So what's the probability that you return, or whatever that was? They didn't really say what that was. I guess your sales or whatever is less than $200. Well, it's the area from here all the way up to there. Except we don't have to use $200. We could use the 2 and look it up in the Z table. So yeah, appendix table E2 has the cumulative standardized normal distribution, which means just what's the cumulative area from minus infinity up to here. So let's see, yeah. So it gives the probability that you're less than a desired Z value. So like that last one, well, still got it wrong here. That says that the probability of this return falling in here anywhere, in other words, the probability that my return is less than $200 is 97%. Yeah, 97.7%. It's pretty, 98%, right? And you look at the bell curve right away. You say, yeah, that makes sense, doesn't it? I mean, we knew half of it's over here already, and we're way, we're not 1 standard deviation. We're 2 standard deviation. We've already got past that portion too. There's not much left up here. In fact, there's just 2% left up there. We're out pretty far. And if Z were 3 or 4, we'd be out there, there'd be nothing left. So this is going to be able to let us answer. So already you can answer a good question. Well, if what's the probability that the return will be less than $200, or the cost will be less than $200, or whatever out of this process? Well, pretty darn high. But suppose it was a stock or something I was buying, and you were asking me, what's the probability that it's over $200? Well, that's pretty darn low. That's 2% chance that it's going to be over $200. Now you're right. I know you're thinking, well, what if this changed? What if this were 100? It's a lot broader standard deviation, right? Well, yeah, this would change, because remember our Z-score would now have been 100. That's the mean. Let's see, it would have been 200 what we're looking at, minus 100 over 100, and now our Z is 1. So we moved way back over here. Much lower probability, much higher probability that you'll reach 200 then, because, the thing's fatter. So let's work some problems and see. Ask these questions and calculate. Okay, so where did I get that number? Yeah, where did I get the 97% or 98%? Did I integrate that density? No. Go to table E2, like they said. E2's in the back of the book, page 770 something, I think. I've written it down for you. And the way the table is organized is you've got, the first decimal point is in this row. So we were looking for 2. The second decimal point's in this row, and the value's in here. So this is 2.00, right? Is that. If we had 2.01, you would have gone to here. 2.02, you'd go to there. And in the problems I work, I'll pull the table up and actually show you the first few. In fact, it's here. I've got it. It's also on line 2. Yeah, there's table E2. So let me scroll down. We'll just look at 2. Don't make a mistake. We're on the positive side, right? We're not on the negative side. 2.00 is here. There's that 98%. 2.01, 2. We're getting more and more as we get out here. Get more and more and more. We're capturing. We're getting all pretty darn close to 1, right? As we get up to 3, 4, we're sucking up the whole distribution out here. 99, 75. It's getting bigger, bigger, bigger. And then I think when you work some of these, you'll get a feel for how this works after you've played with it a little while. So let's see. That's what we'll do. How do we find probabilities? Yeah. Find the probability that X between A and B. Draw the normal curve. They're telling you to draw this so you can get an idea of where you're at. Take X to Z, use the table, and get your Z. Get your probability, or we can do it in Excel. Norm dist and norm inverse will take you backwards. All right? Here we go. So here, back to the internet problem. So let's say we're going to download an image, and we found through downloading a bunch of images that our download process takes 18 seconds with a standard deviation of 5. So what's the probability that any random image out of this process that you download is going to be take less than 18.6 seconds? So that's a reasonable question, right? We've observed this, we've measured this, we've done this experiment, we understand the mean and the standard deviation experiment. Now we're going to ask ourselves, because maybe this is important, maybe after 18.6 seconds everybody leaves your website and they hate you, or your alarm goes off or something like that. So we want to know what's the probability this is going to happen. Let's do it. So we've drawn our picture. This is the X world. And remember, we're going to translate it over to the Z world. Why? Because we got a table of Z values. We don't have a table of things that have a mean of 18, a standard deviation of 5. And the translation was very simple. You relate your value to your mean with respect to your standard deviation. You get 0.12. So here it is in the Z world. Yeah, so your world, mean of 18, standard deviation of 5. The Z world, mean of 0, standard deviation of 1. 18.6 in your world is 0.12 in the Z world. So now the question is the same. The question asked, what's the chances of you being less than 18.6 is the same as asking what's the chances of Z being less than 0.12. So we go to our table, 0.102, there it is, 55%. And from the picture, does that make sense? Yeah, it does. Always ask yourself that, right? We know 50% is up to the middle. And we were slightly above the middle. It was 18 seconds was the mean. We were asking 18.6 seconds, so it should be barely over, 50% probability that we'll get that image down in that time. Now, if it was way out here, 50% would have been a lousy answer, right? So, and if it was less than 50%, we know we did something wrong, because it's got to be at least greater than 50%, because we're on this side of the average. We're adding up from here to there. And then again, you don't have to use the table. Excel will do this for you. I'll show you that too. Okay, now here's the oxy question. Yeah, what's the probability that it was greater than 18.6 seconds? Well, obviously it's 1 minus that probability. Okay, so now they've covered in the other side. Right, so there's 1. It's the whole area. We know this area was that from the previous problem, so yeah, there it is. Right there. Makes sense. 45% chance that it's going to take longer. So yeah, now we want to know, hey, like I said, what's the probability of it occurring just in this range? Maybe that range is important for us for some reason. Okay, so now it's just the difference between the two, right? So asking the question, what is the probability in your world of it between 18 and 18.6 is the same as asking what's the probability in the Z world of it being between 0, because this is the mean, and 0.12. So now we can go to that same Z table, just like we've had. Look them up. At 0.12, it was 54.78. That's here. Yeah, probability of 18.6 is the same as the probability of Z between 0 and 0.12, which is the probability of Z less than 0.12 minus the probability of Z less than 0, right? Less than 0.12 is all of that. Less than 0 is all of that. So we can look the 0.12 up in the table, 0.5478. We could look the 0.0 one up in the table, or we could know, right? If you're right at the mean, it's 50%. But we'll look it up, that's fine, it's in the table. Subtract the 2, 0.0478. So that says the probability that's in that teeny little range is about 5%. See, now you can start seeing how we can use this. Now, that's all we're going to do with it in this chapter, those kind of calculations, answer these probability questions. But what we're going to wind up doing in the future is when we get to looking at samples and trying to make a decision about the sample, we're gonna look out here or out here. And because we're gonna get a sample, we're gonna have a process that we think we understand what the mean and the standard deviation is. And we're gonna get a sample, and maybe we have a mean of the sample, and we're gonna ask ourselves, is this important? And you know, if we think our process has a mean sitting here, and we got a sample and the mean is right here, well, chances are that's probably right. You know, things are going like we want to. But if we got a process where the mean is here, and I've taken a sample, and it sits out here, well, chances are that might indicate a problem, or sits down here, that might indicate it's a problem. And we have to be able to quantify that and understand. And is this a problem, or is this just a random outlier? Okay, we'll find it out. But for right now, for this chapter, all we're going to do is assess probabilities of being in ranges, or probabilities of things occurring relative to a normal distribution. So here, let's look at the back side just for an example. Suppose X is normal again with 18 standard deviation of 5, so we've got the same process. So now, what's the possibility of being in this sliver? 17.4 to 18. Now, you see what they're picked. You know, before we had 18 to 18.6. That was a 0.6 away. Here we got 17.4 to 18. That's 0.6 away too. Why do you think the probability is going to be? It's going to be the same, right? Now, we'll calculate it the same way. The numbers won't look the same, but yeah. So here we've got probability is 17.4 to 18 is minus 0.12 to 0. Yeah, because we're down here in the Z world, which is the probability of 0 minus the probability of less than minus 0.12, which was the half minus 0.4522, which was the same old 5%. Yeah, it's symmetric, so you would expect that. It's going to go that way as you get smaller, or you can move that around. Yeah, and here they're showing the X world. There's your Z world again. And again, we go to the Z world because we've just got one table. And I don't want a book full of 100 tables for all the different means and standard deviations I could possibly have. In fact, it wouldn't work. There's an infinite number of them. It just wouldn't work. Let's see. So now they're going to take a pause, kind of a little bit of a deviation. Now we've talked about the normal distribution. We've talked about calculating probabilities. Now they want to kind of go on a little deviation and say, well, how do you test? How do you know if you have a normal distribution? How do I know if I've got a set of data that this is normally distributed and I could use this normal distribution? I'd hate to do that. If I have a uniform distribution and everything has an equal probability, well, it doesn't look like that at all. My probability density function looks like a rectangle, not that. I don't want to use any of these normal distribution probabilities on that type of data set. So how do we know that? Well, one way is you could just heuristically look at your data, right? You could take a mean and a standard deviation, look at the table and go plus or minus one standard deviation and say, hey, does it look like I have 68% of my data in there? Okay, that's good. That's a good question, yeah. Or we could go out even further, look at 2 standard deviations, 3 standard deviations, just to see if our data looks like it's normally distributed. It wouldn't have to be exact. You wouldn't have to sweat if it was 70% or if this was 93%. It probably, it's close to normal. So these are one ways you can do it. You could look at these. I think I did. Yeah. Okay. You could look at a box plot like we've done, or we could look at these. Call it, and I think they show that in here. I can't remember now on the view graphs. They show this. It's called the normal probability plot. If not, I work with Paul to show you how to do that. You could actually make a plot to illustrate whether your data are normal or not. We'll see how they show it. So now what's this? So now you might want to ask yourself the reverse question. We've asked ourselves, given a certain value of X or Z, what's the probability of that one being obtained? Well, we might go backwards, right? I've got a certain, I want a probability and relate that to an X or a Z. For example, I'm taking a test. What score corresponds to the top 10% out of this group? Okay, I don't know. Am I in the top 10%? Or IQ, right? Yeah, I got a whole bunch of IQs I've measured, and we're assuming they're distributed normally. And so, we want to say, well, the top 2% of the people, what's the cutoff IQ for those folks out here? So it's the backwards problem. Given a probability, how do I get a value? So how do you do that? Okay, let's see. Well, one, we're going to be working, we might be working in the Z world, so one thing is we have to translate back to our X world. We don't want a Z answer, 1.28. There's no unit that's no good or something. So all you did there was just solve this. Just rewrote it. So multiply by mu times sigma and add mu. So X equals mu plus Z times sigma. Well, of course, Z was the number of standard deviations you were away from the mean. X is the mean plus Z times the number of standard deviations. So you just go backwards. Okay. So here, let's do a problem. Let's see. So X is the time to download this picture. X was normal again at 18 seconds for the standard deviation of 5. So we're still working with our same image downloading problem. So now the question they're asking, well, hey, what value of download time that 20% is of the things are less than that? That's a nice question, right? Hey, 20, the fastest 20%, what's their download time? Where do they fall? Okay, so yeah. So here's that question. In your X world, we have a mean of 18, standard deviation of 5, and hey, what's this value? 15 seconds, 14 seconds, 13 seconds? What's the value where below which 20% of them fit in? So, well, let's answer it in the Z world, and then we'll translate it back. And again, why don't we answer in the Z world? Because we got a table with the Z. We don't have a table with 18 and 5. All right, so let's see. Now, so working backwards, you can, you dig through the table. Obviously, we've got to work backwards, right? So we're looking for 20% in the table. We're not, before we had a Z value, but we went and looked at the percentage. Now we got a percentage, we got to find the Z value. So you see here, they're picking the closest. Yeah, I'm fine, that's good enough, close enough to 20. If we use Excel, we can plug 0.2 smack into it and get it right out. So here, we'll use that. So what that says is 20% pretty much corresponds to minus 0.84. Remember, that's the first digit. Here's your second digit. Now, does that make sense to you? Yeah, right. We knew it had to be minus because 50% is up here. That's 0. So minus, had to be minus. And yeah, kind of thinking about that normal distribution. Remember that little picture we had, 68% was in plus or was between -1 and +1. So yeah, you think, well, that means you got kind of, 15% over here and 15% over there after 1. So yeah, that should be close to -1. And I think after you work some of these, you'll get a feel for, yeah, should that have been, minus 10? No, that's way too small. Or should it have been minus 0.5? Well, you'll get a feel for that after a little while, I think. Let's see. So now to go back, right, what was the X value? Well, our mean was 18, our standard deviation of 5, our Z was minus 0.84, so it's 13.8 seconds. So the answer to the question was, yeah, 20% of the images will be in your hand by 13.8 seconds for this process. This process that has a mean of 18 and a standard deviation of 5. So you can start seeing how you can use this. You can turn around and ask the other question. God, the slowest 20%. How long are they going to take? How much am I going to make people wait and stuff? That might be more useful than the quickest in this case. But you can start seeing where this has some value. All right, so again, not every data set's normally distributed. We know that. You were talking about grades that had 2 humps. And we're going to talk in class about exponential and uniform and log normal distributions. But many things are normally distributed. Many things. And you can also assume that many things are normally distributed. So how do we find that out? Okay, well, we can look at these heuristics like the interquartile range, that 68% thing we were just looking at. We could do a box plot. We could do those descriptive summary things. Look at the 6 sigma range. We can do all of that kind of stuff to evaluate things we looked at last class. Yeah, we could say, hey, are pretty much 68% of between plus or minus 1 is 80% between plus or minus 1.28, and 95% between plus or minus 2 standard deviations. These are, heuristic things we could look at, or we could do this normal probability plot. And if you do a normal probability plot and it comes out as a straight line, oh, well, the data are normal. If it's not a straight line, they're not normal. And how far off does it have to be? Well, let's see, I think they show some pictures. Let's see. That the book does. Let's see. Yeah, there. Yeah. So right. So here's a uniform distribution. Here's one that's right skewed. Here's one that's left skewed. You kind of have to decide, how important it is that you be exactly normal. All right. So I'm going to give you the directions on how to do this, and then I'll show you with an example too. Because when you first look at it, you might say, what are you doing? So you order your data, and you would find what Z would correspond to that particular data number. So if I order my data from low to high, and I say I've got 20, 30, 50 data points, and you say, well, if it were normally distributed, where would those data points be? And we know if it's normally distributed, and I order them from low to high, you ought to have one here, one here, one here, and they start getting more of them in here, right? And then they spread back out again. Whereas if there's a uniform distribution between the low and the high, I would just have a bunch of the same number of data points, everywhere. And so by ordering them from low to high and coming up with this Z number that corresponds to this, and plotting these values with respect to Z, you should get a straight line. That's what they're saying. Plot the pairs of points with the X value, and their Z value is on the X-axis. The data point actually is on the Y-axis. And if it's a line, it's a normal set of data. So again, I'll show you the mechanics on how to do that. I think when you read it, it's not clear. I think you say, oh, that's not clear what you're supposed to do when you read it on the view graphs. Now, the book, in the section on normal probability plot, shows you how to do it, shows you how to calculate those Z values. It is very clear. And my example will show you too in Excel. And I did it for a uniform, and I did it for a piece of normal data. So I think we can discuss it too when we get to the problem. So it's problem 622. So I'll work it, and we'll talk about this again. But anyway, like we said, that would be a normal set of data. And this perhaps not, and this perhaps not. It's enough of a deviation. This one certainly not. And so, yeah. And how far of a bend do you tolerate? Well, that depends on what it is you're using this to calculate. It's the criticality of some pile of radioactive material. I don't know. I'll be careful. If it's just some estimate I've guessed on a project manager, well, I'm not really okay with it. That sort of thing. So you can decide. We could do a box plot. This set of data is not normal. Why? Because the normal distribution is symmetrical. Remember, if it's symmetrical, the box is going to sit in the middle, and these two guys are going to be the same on each side. So that might be a simple way to do it. Yeah, you got these statistics. Yeah, so they're looking at here. Let's see. Here, some bond funds here. There's 77% of them are within one standard deviation. And normal is 68. So you're starting to say, no, I don't think that's normal. That's probably not close enough. And so maybe I don't want to evaluate probabilities on this set of data using a normal distribution. Skewness is 1.7. Normal distribution, each of those are 0. So you start saying, hey, this set of data that they randomly picked that had this box plot that they showed up here doesn't look, it's very normal. Well, yeah, it's not. It's skewed to the right. And again, what's a right skewed thing representative of? Well, remember, it was like incomes or housing prices, things that have a bunch that occur around here around some average, but then there's some weirdos that are huge, giant mansions that are high priced, or people buy those mansions that have high salaries, and so yeah. And if you were maybe again wanting to model this or do something with it, well, maybe you could throw out some of these outliers, bring this in, and then use a normal distribution for just those or something, and make some conclusions about those from a normal distribution if you wanted to, recognizing that you've thrown away those outliers and that part of the data. Yeah, so here's that normal probability plot. Yeah, look, it's not a straight line. These are the outliers, those ones, those big right skewed things, they're the ones that are making it, like I said, they're the ones that make it not be normal, right? If we threw those out, if we said, let's throw these outliers out, the real high ones, well, that's not too bad. You might be able to do, like I said, call it normal if you wanted to. All right, let's see. So, yeah, tons of right skewed. They have more values concentrated in there, the mean than they should have. Yeah, it was tighter. Range is larger. Yeah, the normal plot's not a straight line. Overall, yeah. So overall, you'd say, yeah, that's not a normal set of data. Don't use a normal distribution to answer questions on that. Okay. So now we're going to switch gears and start talking about a different distribution because you might want to model something else in another way. So here, the uniform distribution is one I use when I don't know much about a process, right? I've got a minimum and a maximum. And I'm trying to pick a value in there, what's the time it's going to take me to do this. It's either 15 seconds or it's 20 seconds. That's my max, somewhere in between. So the uniform distribution will just pick a number in between there with equal probability. Might be 16, might be 13, 15 and a half. It'll fit inside there. But I do use this distribution a whole lot to feed an inverse normal distribution if I'm trying to pick somebody, if I'm trying to create data that's normally distributed. And I'll show you how to do that because you might actually want to do that. You'll make yourself your own normal distribution with a mean and a standard deviation in Excel and use that like I did to fake data or to fake some process. And so if you feed a rectangular distribution into the inverse normal, then you'll be randomly picking off of here. And so I'll show you how to do that in case you need to. So here is the density function for a uniform distribution where A is the minimum, B is the maximum. So you can get an idea, right? So say if A were my minimum here, this uniform distribution, B were my maximum, that says is this density function here, this is 1 over B minus A. Yeah, that's not too startling when we said, this area under here has to be 1. So, yeah, B minus A times 1 over B minus A equals 1. And so think about what that's saying. If I had a distribution from what, 1 to 3, well, like I'm going to say A is 1 and B is 5, and that says that this has a probability of 1 out of 4. Of obtaining some of these numbers in here like that, yeah. Yeah, that makes sense. Yeah, if I was having a discrete distribution, say, yeah. Think of it that way, yeah, I have 1 in 4 chance of getting any of it. The mean is right here in the middle. Okay, and there's the standard deviation. Again, that's not particularly obvious. A little bit of math involved coming up with that. It's not, the mean is obvious, right? The mean is going to be right here in the middle, B plus A over 2. But that standard deviation, I have to do some math. And again, that would be the type of thing you would get in an advanced statistics class. They'd sit up here, we'd drive how we got the standard deviation of this, and then we'd go use it in something else. I don't think for our purposes that's what we want to do. Yeah, there's your picture of it. Yeah, so let's see, here we got a uniform probability distribution from 2 to 6. Okay, so yeah, 1 and 4 here. There's your standard deviation. Yeah. 0.1, so here where our mean is 4, right? Yeah. Okay. So let's see. Yeah. So what's the probability that we're between 3 and 5? Yeah. It's a half. Does that make sense? Of course. I'm going from 2 to 6 now, and what's the probability that I'm going to sample out of this distribution and have a number between 3 and 5? That's 50%. That makes sense. You can calculate it that way. But chances are you don't, and you might not care because you could just use Excel, produce a random distribution between 2 to 6, and use those numbers in some process if you want to. But you have to calculate probabilities. All right, so now we'll talk about the exponential. What they're trying to do now, you wonder, why are they throwing all these distributions at me? Because if you are making a model of a process, you might need to choose the appropriate distribution when would that happen? Like the example I gave last week, if you're doing simulation model, and a simulation model, you know, you're using this piece of software to model a manufacturing process. So you've got raw materials that come in, people go and move the raw materials, they put them on a machine, the machine machines them, some other people moves them off the machine, they assemble it. You're building a model of this, and when you do that in these simulation modeling softwares, the times are always, well, the times could be fixed. It takes exactly 1 minute to unload the machine and move the parts over here. But we know that's not true. You know, it takes 30 seconds, maybe it takes 5 minutes. There's some distribution. So the beauty of these kinds of software is that you can model all these things as random distributions. Why would you want to do that? So that you can get an idea what the randomness is in your process, right? No one comes in and says, it takes exactly 2.35 days to make a part. They don't say that. It's going to take there's a range. And especially over time, or if machines fail, or if people have variations, or you have 5 workers, and worker A can get things done in 3 minutes with a standard deviation of 1 minute, and worker B takes 10 minutes with a standard deviation of 5 minutes, well, yeah, if worker A and worker B are in there, you're going to get different results. But overall, you'd like to know what the sum is with A and B on different shifts, so you'd have to build a model to evaluate this. Well, within that model, you're going to have to pick either constant times or distributions. Well, wouldn't you like to pick ones that make sense? Yeah, so why would you pick an exponential time? Well, people, researchers, have discovered that, in general, inter-arrival times follow an exponential distribution. What's inter-arrival time? Like, if I'm a bank, and I'm sitting there and I'm a teller, I'm waiting for customers to come, that customer showing up follows an exponential distribution. Why? It just does, right? And they found that. They've studied that, and they realized it. So if this is the arrival of UPS trucks at the UPS sorting center, well, I might pick an exponential distribution, because it's the one that's most appropriate. But if it's how many times I'm going to drop a package in the wrong spot, well, maybe that's a normal distribution. We've kind of, maybe we don't know. It's a new process. I have no clue. Well, maybe I'll pick this uniform distribution because at least some expert says, well, hey, I think it's going to take at least this long, but probably not longer than that. Well, okay, we'll use that one. And then maybe if I don't have any clue, well, I'll just pick a number out of the sky. But that's probably worse. At the very least, you think you pick that. At the very least, I can usually come up with a low and a high value. And I think you mentioned before with the engineering econ, was talking about triangular distribution. That's a common one too. That's similar to this with a low and a high.